Oh, Bob, getting second. It's gonna be North Carolina versus South. 16 points at all. And you? No. I have to move football, right? That's my really. So. You don't know, okay. What's your favorite Jordan shows? They had 14 points at halftime. They didn't score for 14. Really like the regime. No, like
Okay, if you guys can turn to page 10, I know you've already finished this problem as part of your homework, but I want to make sure that we understand the process of limits. So the first thing that we do for any limit problem, especially if it's an algebraic problem, first thing we do is always what? First step. Yeah, plug in, right? Let's evaluate. We don't know, well, let's just figure out what's going on. We don't know if there's a hole there. Is there asymptote? Is there, is it continuous? We're just doing information gathering at the beginning. So we're going to plug 2 in, see what's going on. And then we can do further evaluation. F prime of 2. This is the F prime graph. So F prime of 2 is just what? Just 0, right? So 0 over e to the 0 minus 1. So denominator, we get what? 0 over 0. Now, 0 over 0, what that tells us is that there's a hole. This is indeterminate form. The value doesn't exist there for this graph, but the limit does. We just have to find what that limit value is. We just haven't found it yet. So typically, we would try to maybe look for common factors that can reduce, but this is one of those problems that we're not going to be able to just rely on just looking for common factors and reducing and reevaluating. We have to do something to get us to use L'Hopital's rule. So L'Hopital's rule tells us that for limit problems, that gives you 0 over 0. Another option to help you get down to a real number is you can find the derivative of the numerator and denominator. That will give you a different version of the expression. You can then reevaluate and hope that the evaluation will lead you to a real number, because if it does, we can stop the problem and say that's our limit. So let's apply L'Hopital's rule. Okay. What's the derivative of the numerator? F double prime. Okay, and we can find the derivative of these separately. This is not quotient rule where we got to do the whole mess. We're not interested in finding the derivative. We're using the derivative feature to help us get to the limit value that we're looking for. Okay, what's the derivative of the denominator? E to the u becomes what? E to the u times u prime. So e to the x minus 2 times 1. Yep, that x minus 2 not going to produce anything but 1. And then the 1 goes to a 0. Yep. So this is our updated expression using L'Hopital's rule. Now we can reevaluate and hope that it no longer gives us 0 over 0, but hope that it gives us a real number. So replace every x with 2. So f double prime of 2, what is that asking for us to do from the graph here? Find the what? Slope, right? What's the slope of this line segment? 2, right? Pick 2 points, just do rise over 1. I go up 2 over 1. That's the slope of 2. Denominator is e to the 0. E to the 0 is 1. So my limit is 2. Okay. Something as a side note is on the AP exam, they're really particular about when you use equal signs. We see if you use equal sign, both sides have to be equivalent to each other. And that's not the case with some of these terms. So what we want to do is you want to use arrows to indicate to the grader that you're just telling them what the next step is, but you're not committing to both sides being the same. Okay. I wouldn't take off any points on my assessment, but on the college on AP exam, that's one of the nitpicky things that they we realized as graders in the past. Now, I do want to point out something with zeros, because just because you see zero doesn't necessarily always mean the same thing. So for instance, let's say we find the limit and we got 0/5. How would you interpret that? That is a real number. That is 0. We can stop. That's a real number. Okay. What if we get 5/0? There is no limit, right? Undefined. There's a vertical asymptote. The limit does not exist. Now, if it's a one-side limit, that's a different story. But usually with these problems, it's not going to be a one-side limit. So limit doesn't exist. We stop. Nothing more to do. But if we get 0/0, there's a hole, but the limit does exist. We just have to keep going. Typically, L'Hopital's rule will help us get to a real number. So depending on where the 0 is in the fraction, it's going to mean something completely different. So I want to point those distinctions out to you. Okay, let's go to page 11. Okay, a sandpit is being filled with sand whose height at any time t is given by a differentiable function h of t with domain between 0 and 12 minutes. Let h prime be a differentiable function representing the rate at which the height of a sandpit grows in inches per minute. So let's pay attention to that. It is known that h prime is increasing on its entire domain. Values of h prime are given as select values of t in the table above. The height of the sand pile is 40 inches at t equals 9 minutes. Okay, estimate h double prime of 2. Let me just kind of talk about this table so we can kind of visualize what's happening here. So that means 0 minutes in, the sand pit is being filled at a rate of 1 inch per minute. Right, 1 minute in, that rate is increasing. Right, it's increased to 2 inches per minute, and then 3 minutes is coming out faster, coming out more, 5 inches per minute, 7 inches per minute, 10 inches per minute. So we see that the rate is growing. That sand pit is getting filled up faster and faster, right? So, or that sand pit height is growing faster and faster. You kind of imagine that since more is getting filled in over this time period. Okay, estimate h double prime of 2. Right. Now, h double prime, what's the relationship between h double prime and h prime? Okay, so a couple of things, right? We can say derivative, we can say rate, we can say slope, right? We can't find the derivative because we don't have a function to do, but it's only asking for estimation. So we can just get away with finding what? Finding slope. All right, so what do we need to find slope? What information do we need to build slope? 2 what? 2 points. Now, which points would you choose? Should we use the entire interval? Right. Which one do you think? So I would say these 2 order pairs here. 1, 2, and 3, 5. Why is that? Yeah, I would say it's because it's the closest to our source, right? The closer we are to our source, the less likely that drastic changes can happen, right? The further we are from our source, the more open we're susceptible to drastic changes. And the more drastic change that can occur, the less accurate we're going to be. Now, we don't know exactly how accurate this will be, but typically the closer we are to our source, the more accurate we are. Right? So we're just going to use the two order pairs that are closest to our source. And squiggly line to indicate it's an approximation. So we can just say the change in h prime over the change in time, right? So h prime of 3 minus h prime of 1 all over 3 minus 1. Okay. All right, let's find the values here. H prime of 3 is, yep, so 5 minus 2 over, yep, and that reduces to be what? 3 over 2. Okay, what's the new unit of measure here?
Inches per minute.
Good, inches per minute, right? We have a rate of a rate, so inches per minute squared. Now, in the context of this problem, what is that information telling us about what's happening? Say again?
Rate at which it's being filled is increasing.
There we go, right? So we want to be able to indicate that there's a rate of a rate going on, but we don't want to quite use the word rate of a rate. That's not as clear as graders would like to see. And we don't want to use words that are out of context, like acceleration, right? Acceleration is good for particle motion, but it doesn't quite fit what's going on here. So we want to be able to say either rate is changing, or rate is increasing, or rate is decreasing. In this case, it's increasing because we see that positive 3/2 inches per minute squared. So the rate that sand is being added is increasing, right? So it's getting filled up faster and faster at a faster and faster rate, right? So we're basically indicating that there's an increase in rates. And so we want to say that the rate okay, so the rate of change of sand pit height is increasing by 3/2 inches per minute squared at t equals 2. All right, and the key words that we are want to make sure that we indicate is the fact that you got rate increasing. Okay, that's basically tacking on that second derivative. First derivative is rate of change. The increasing of that is where that second derivative is coming in. Okay, part B, use the right Riemann sum with the subintervals given in the table. So that means we want to use every subinterval spelled out by the table. Approximate the definite interval from 0 to 12 of h prime of t dt. So we know Riemann sums is going to be area, width times height. So we're going to use every subinterval that we see here. So I'm going to spell out every subinterval, build out every width. Okay. All right, let's see. How do we find the width of each of our subinterval? First subinterval has a width of what? 1. Second subinterval has a width of, because we do what with these numbers? Subtract, yep. Next subinterval. Next one, 3. Okay, now, what is the area of my first rectangle? Width of 1, height of 2. Why 2? Yeah, right, Riemann sum. We want to choose the height on the right side. If it was left Riemann sum, you would choose 1. For this problem, they would not tell you to actually do middle Riemann sum because there is no middle y value. If they're going to tell you a middle height or a middle sum, then they'll have to give you an odd number of ordered pairs so you can pick out the middle one. You're never asked to find the average of two numbers. Okay, so yeah, so the height for my first rectangle was 2. So squiggly line to indicate an approximation. So width of 1, height of 2. Width of 2, height of second rectangle has a height of 5. Okay, let me just go down the line, right? So we add that up. It gives us 84. And what is our units of measure going to be now? Just inches. Okay. Now, I want to talk about what this means, because it may not necessarily mean that the sand pit has a height of 84 inches. We want to be a little more specific than that. So I want to kind of explore this notation a bit. Okay. Now, if you remember first theorem, if we want to leave it in function notation here, if we want to apply first theorem, what is another representation of this integral from 0 to 12 of h prime? H prime becomes what? Becomes h, right? H of what? What do we do with the bounds? Yep, h of 12 minus h of 0, right? So that's first theorem, right? First theorem says the integral from a to b of f prime will rise up to f. Integral of f del prime rise up to f prime. Integral of h prime will rise up to h. So this is what we found. Okay. I want to talk about what this means. Well, first off, if you know that this is what you're dealing with, then you're not going to make a mistake of saying this is inches per minute, right? Because you know h is height in terms of inches, not inches per minute. Second, we want to be able to phrase this in the proper form, right? What does this mean? Let's talk about what each of these mean. H of 12, what does h of 12 mean on its own? Yeah, the height of the sand pile at 12 minutes, and then h of 0 is at 0 minutes. And if I subtract those two, what information does that give us? Okay. Okay. Or let me give another example. Let's say it was like h of 12 minus h of 4. Okay, I'm just making some numbers up here. Let's say this was 20 inches and this was 4 inches. What is that number going to tell us? What does that tell us in the context of that problem? Yeah.
How much it's changed?
How much has changed, right? So how much the height has changed over that time interval? Okay. I mean, it could be in this case that the height is h of 12 minus h of 0. It could be that it's exactly 84 inches, assuming that h of 0 is 0. But the more clearer way of saying it is that this is the change in height or the change in units over that time period. Okay, so 84 inches is the change in height. This tells us that 84 inches has been added to the sand pit height between the 0 and the 12th minute. Okay. And if we have trouble with this, I think it helps to look at where this is coming from, right? If we can think about what h of 12 and h of 0 and what the subtraction of that is doing, I think it makes it easier for us to come to this conclusion if we can look at this and kind of study this a little bit. Right? I know this is definitely a little more abstract, but now that we have first theorem available to us, we're able to get it into a form that feels more concrete, right? This feels a little bit easier to, more tangible in terms of understanding what it means. Right, in College Board, they love doing this. They love to see if students can come to this conclusion. Yeah, so a lot of first theorem, a lot of interpretation of first theorem for FRQs. We're going to see that a lot, or you can expect to see that on the AP exam. Okay, likewise, if we want to extend that first theorem application how do you think we can evaluate H double prime from 0 to 9? What's a way of writing this a different way? What is this equal to? Good. Good. So looking at this, it's a lot easier to understand what's going on because we have data to get a number out of this, right? What's H prime of 9? Yeah. And H prime of 0 is 1. Yep. So, and then what's our unit of measure going to be? Inches per minute, right? That's easy to tell because we know we're, in terms of H prime, we know H prime is inches per minute. So it's not asking for the interpretation, but we can say that what this means is that between 0 and 9, the rate of sandpit or the rate of sand being added is going to increase by 6 inches per minute. Because it started off at 1 inch per minute and it goes up to 7 inches per minute. So over that time period, it has risen 6 inches per minute. Okay, good. Next page. Okay, part E here. Write the equation of the tangent line to the graph of h of t at t equals 9. Use this tangent line to approximate h of 10. Is this an over or under approximation? Okay, one thing at a time here. Write the equation of the tangent line. Okay, we've seen that a lot of times now. What information do we need to build tangent line? Slope and point, right? Do we know what h of 9 is? Is what? H of 9. There it is. Yeah. So it's hiding inside the description here. The height of the sand pile is 40 inches at 9 minutes. Okay, so that's our point. But we need slope as well. So h prime of 9, this is probably what you were thinking about. H prime of 9 is what? Okay, so that's 7. Okay. So let me just kind of phrase this a different way here. This is telling us that at 9 minutes, the height is 40 inches, but at 9 minutes, the rate of increase is 7 inches per minute. Okay, so we're going to use that data to help build our tangent line equation. So here's my point. Here's my slope. Hey, now typically point slope form, we do this, right? We say y minus y1 equals m times x minus x1. I just want to adapt this to the variables that we're working with. So instead of x and y, what variables are in play here? Yeah, so x, we're going to replace what for x? Oh, and then for y, we'll put h. So I'm just going to making the exact same equation. I just want to match it with the variable that that the problem is using. And I'll replace h1 and t1 with my point, and then build my equation. Solve for h. All right, we have our tangent line equation. Any question? Okay, use the tangent line to approximate h of 10. So this is linear approximation. Sometimes it's a decimal value. In this case, they're just giving you a value that we could plug in. So we'll plug in 10 in for what? And for t, yeah. So we'll just say h of 10. So because we know how much sand there is at 9 minutes, and because we know approximately what the rate is, we can figure out what the sand pile is going to end up being at 10 minutes, or at least an approximation of it. So what is that going to end up giving us? 47. Now, this isn't perfect, but we do know that we're given it's at 40 inches and 9 minutes, and at h prime of 9, we don't know what's happening between h prime of 9 and h prime of 10, but the best approximation we have is 7. So it stands to reason that if we are approximately probably close to that 7 inches per minute, then 1 minute in, after that, it'll probably be around 47. Okay. But again, we know it's an approximation, and that is the second part of the problem. Now, the last part is this an over approximation or under approximation? Right. We know that this is not the exact value, but is this higher or lower than the actual value? So let me explain that a bit. We have to know, basically, is this graph concave up or concave down? Okay. The graph of h. So let's think about what concave up is doing. If the graph is concave up, any tangent line will sit what? Above or below the curve? Below. So anything that I use the line to approximate is going to be what? Under approximate, right? It's going to be lower than the actual value, right? Doesn't matter where the tangent line is, it's always going to sit below the curve. Meanwhile, if the graph happened to be concave down, then any tangent line that I put to that curve is going to be what? Over approximate, right? Any point that is close to that tangent line, tangent point, is going to sit above the curve, over approximate. So the question is, we know we're trying to decide between these two. Does the problem give us enough information for us to conclude which shape our graph is? Okay. What do you see that is telling us whether it's concave up or concave down? Yeah. Another sentence that you see that describes that. There it is. H prime is increasing. H prime is increasing. In other words, H prime is like slope, right? So it's basically saying slope is increasing. So if you look at a concave up graph, slope is always increasing because I'm just doing ballpark, but this could be a slope of -3, then -2, then -1, then 0, 1, 2, 3, right? Slope is increasing. It's always moving towards a positive number. So when you see H prime is increasing, that's enough for us to conclude that H of t is experiencing concave up. If it's concave up, then my tangent line is going to sit below, and so therefore 47 is what? Under approximation. Okay. So the nice thing about us going through these problems is that there's a pattern. College Board, these are the types of problems that they like to ask, because we have every FRQ released over the past, I don't know how many years, and these are the patterns that we're seeing. And the hope is that by the time we get to AP exam, it won't feel like a new test. Hopefully, it'll just feel like something you've seen before, right? These phrasings, you can almost anticipate what they're going to ask you next. That's the hope that we can feel that way when we take our AP exam. Okay, F and G are really popular things that College Board, they like to test students on this type of thing here. So let's talk about this. Explain why there must be a value C on the interval from 9 to 12 such that H prime of C is equal to 8. Okay, let me phrase this a different way. Can we guarantee that between the 9th and 12th minute that the rate of sand added to the pit is exactly, there's going to be a time where the rate that the sand is added to the pit is exactly 8 inches per minute? Yes. Okay. So we have the H prime graph or H prime table. What about this table tells you that we can guarantee that 8? Okay, 7 to 10. And how do we know that there's no break in between that's going to jump past 8? Differentiable, right? So differentiable assumes continuity. So you guys, and this is from all the way from unit 1, but do you guys know what theorem that is referring to? Not Rolle's, not mean value theorem. I know this is a long time ago, so it's okay, but we don't remember. It's called intermediate value theorem, IVT, right? There's no calculus in IVT, but it is something that College Board, that is part of our curriculum. So all it says is if I have a value below my target and I end up with a target above my, or I end up with a value above my target, then there's no choice but for that graph to hit my target somewhere between, right? Or I can go the other way. I can start above and end below, and I'm going to hit that target in between, right? So it's not a difficult concept to understand, but it is a little messy to write out. So let me show you what's one way to represent our answer. Okay, so since H prime is continuous, then by IVT, H prime of C is equal to 8. So we can guarantee a rate of change of 8 because we started off with a rate of change below 8 and we ended up with a rate above 8. So there must be a rate of 8 somewhere between if we're starting at 7 and ending at 10. Technically, you don't have to reference IVT. You can just describe the conditions of IVT, and that will be enough to earn you full credit as well. And so IVT is one of those things where it's easy to understand, but it's a little convoluted. It's a little bit difficult to put into words because you know we just want to say something is going to be between two numbers, but it just comes out a little wordy. Okay, look at part G because what they're asking seems very similar. Explain why there must be a value C such that H double prime of C is equal to 3/4. Right. Now, do we have a table that we can compare and look at H double prime values? We don't, right? So, you know, IVT is not going to quite work here because we don't know what's happening before H double prime of 0 and you know, we can't look at a chart or table or graph and see, okay, this is something starts below 3/4 and ends up above 3/4. So we can't rely on IVT, but we do have H prime though. What's the relationship between H prime and H double prime? It's the derivative, right? So if I want, it's another way of saying derivative is slope. So if I want to look for a slope, or if I want to guarantee a slope, what is that? That's another theorem. You guys mentioned it before.
EVT.
MBT. This is mean value theorem. Okay, this is mean value theorem. So I do want to point this out because if you're at the level that the problem is asking about, then IVT is perfect because you can just look at the data and just see, okay, is it going to sit below or above? But if you're not sitting at the level of the data, and if you're a rate of change away, then if you want to guarantee a slope, then you want to think in terms of MBT. Okay, so the idea is that if I can find the slope of my H prime to be 3/4, then I know there must be a guaranteed 3/4 somewhere along that curve. Right. So we're going to find the slope between the endpoints. So the slope between on my H prime graph, right? We know H prime of 12 is 10, H prime of 0 is 1. I do change in H prime over the change in time. So imagine this was the H prime graph. Okay. Then if the slope between the H prime between 0 and 12 is giving me 3/4, then there's no choice but the graph to experience an exact moment of 3/4 slope along that curve. And we know the function is differentiable, so it's a smooth curve. There's nothing strange happening between the curve. There's no asymptote or hole or sharp turn. So there exists a C on the interval from 0 to 12 where H double prime is equal to 3/4. So I want you guys to kind of look at these two things here. And it's nice that these are next to each other. So we can kind of see, okay, the phrasing is almost identical, but because of the data that we have to adjust accordingly, right? If we're at the level that they're asking about, we use IBT. If we're at a level that is a derivative away, then we want to use MBT. Okay, I'd like to get started on page 13. Page 13 is going to feel like what we did on page 7. So hopefully things will begin to look more and more familiar because of the reps that we're getting in through these days. Okay. All right, page 13. All right, so just like page 7, this is a table, there's a graph, there's a function, there is something that's identifying this as the derivative of some graph. So part A says find the slope of the line tangent to the graph of f at x equals pi. So it's just asking for the slope. So if I want to find the slope of a graph, I'm going to find what? Derivative, right? And then from the derivative, I can plug in pi, and then there I can get the slope. All right, so let's kind of think about what the derivative is. Cosine of u becomes what? Negative sine of u times u prime. E to the u becomes u times u prime. Okay, so let's see if we can build out our derivative. Okay, replace every x with pi. And then we're going to use unit circle values to try to get it down to a number or simpler numbers. Sine of 2 pi is same thing as sine of 0. So sine of 0 is just 0. 0 times 2 is just 0. Sine of pi is 0. E to the 0 is 1, right? And then cosine of pi is close, -1. Okay, so we're just cleaning those values up, getting it down to a number. Then let's look at part B. Okay, part B says, let K be the function defined by K of X equals H of F of X. Find K prime of pi. Okay, let's find K prime of X first. So if I want to find the derivative, look at how this function is set up here. What rule do we need to do to get to our derivative? Good, chain rule. Outside derivative times inside derivative. So what's outside derivative going to be represented by? Good, H prime of F of X. We don't change the inside, right? We leave it alone. Times F prime. Okay. And then once we have that, we can replace our x's with pi. And just be careful with chain rule. We're not going to be able to get to the slope value in just one step. We kind of have to gather information. We got some nested pieces inside each other. So we got to kind of start from the inside and kind of work our way out. Now, I underlined these two parts because these are the easier things for us to evaluate. Do we know what f prime of pi is? Yeah, we have that from part A, right? So we can carry that down. How can I find f of pi? Plug pi back into the original. Yeah, so we have our original function there. Okay, so we'll do that. So f of pi is just cosine of 2 pi plus e to the sine of pi. Cosine of 2 pi is same thing as cosine of 0. Cosine of 0 is 1. Sine of pi is 0. E to the 0 is 1. 1 plus 1 is 2. So we have our f of pi figured out. That's a piece that we need. Now, last piece of the puzzle there to get to a number. H prime of 2. What can I use to find h prime of 2? Yeah, the slope of the graph, right? I have my h graph. So this, if I can find the slope of this line segment, I can find the slope at that point. What's the slope of this line segment? Yep, down 1/3, right? Rise over 1, -1/3. Okay, so we put all that together. And we have -1/3 times -1, which is 1/3. Okay, I want us to end class with part C, and you guys will finish the other 2 pages. Up to page 14 on your own. Let's talk about part C. Let m be the function defined by m of x. M of x is defined as g of -2x times h of x. Find m prime of 2. Okay, before we get there, let's find m prime of x first. Get to m prime of x. Look at how this is set up. What do we need to do to get to its derivative? Product rule. Do you see how this is different than k of x? These both have 2 different functions, but this one is one inside the other. This one, they're outside of each other, being multiplied. So that's product rule. So we'll do product rule here, but then within g of -2x, there's a little bit of what? A little bit of chain. Okay. So we have a couple of rules going on, but the big rule that we want to first establish is that there's a need for product rule. So I'm going to spell out product rule there. I'll call the first thing I see f. I'll call the second thing I see g. F prime g plus f g prime. Okay. Now to get to f prime, I need to get to this derivative. So tell me what is the derivative of g of -2x? You said chain rule, so what would this look like? Good. G prime of -2x, that's the outside derivative times -2. Good. So that's want to make sure that you guys can see that. That's the hard part. Building out the derivative, because now it's a little bit easier. Now just replace every x with what? With what? 2. Yeah, replace every x with 2, and then you're just gathering the data from above. Either you're pulling from the table or you're pulling from the graph, and you're just trying to get that down to a number. Okay, so tomorrow I'm going to check pages 11 through 14, and we have another day tomorrow to a full class period to continue to get more practice with some of these AP problems. Okay, all right, computer folks. Okay, 10. Okay, thanks.